Hello friends, today we are going to look at another topic in numerical methods, which is Newton's method. Newton's method is a popular method that can be used to solve nonlinear equations. And Newton's method is also called Newton-Raphson method or the tangent method. Newton's method, like the fixed point iteration method that we have seen before, belongs to a group called open domain methods, unlike the closed domain or bracketing methods. The nonlinear function f of x equals 0 could be an algebraic equation or a transcendental equation. An algebraic equation typically consists of functions of x, as in x or x squared or powers of x. Transcendental equation can have, in addition, logarithmic, trigonometric, or exponential functions. Some examples of nonlinear equations are given below. The first one is an algebraic equation and the second one is a transcendental equation. Our objective is to solve these two nonlinear equations using Newton-Raphson's method. The algorithm for the Newton-Raphson's method or the Newton's method is given below. F of x is the curve. We need to find the root for this curve f of x. The exact solution or the exact root is given as alpha. So what we need to do is we assume an initial x value, which is x of I, and we evaluate the slope of f of x at x of I. So that which is f dash of x of I, which is equal to the slope of f of x at x of I, which is equal to f of x of I plus 1 minus f of x of I divided by x of I plus 1 minus x of I. But by looking at the graph at the left hand side, we know that f of x of I plus 1 equals 0. Substituting this into the first equation, we get x of I plus 1 equals x of I minus f of x of I divided by f dash of x of I. So the iteration stopping criteria is modulus of x of I plus 1 minus x of I should be lesser than or equal to epsilon 1, which is our tolerance criteria, which is typically a very small value. Or we can use modulus of f of x of I plus 1 should be lesser than or equal to epsilon 2, which is another tolerance criteria, which is also a very small value. So considering our two examples, we can apply Newton's method here. The function f of x is given in the first line, and f dash of x is the derivative of x, and we need to evaluate x of I plus 1 for the first iterative step, which is equal to x of I minus f of x of I divided by f dash of x of I. So we repeat this procedure to get a more accurate solution. The same procedure can be used for the second equation as well. Now we go to Matlab and try to run this program. So the initial value x is considered as 0. The number of iterations n equals 100, and the algorithm is given here. We're going to solve or find the roots for the transcendental function, transcendental equation first. We can run this, and it takes only 6 iterations to find the root for this problem, and the root is obtained as negative 0.768039, and at this value f of x is almost 0. We can look at this graphically. So our root is somewhere there. The numerical solution is generally more accurate than the one we are reading graphically. We can even go and solve for the root for the first equation, which is the algebraic equation. Let's try to solve the first problem. In this case, again, it takes about 6 iterations to find the root, and the root is obtained as 0.381966, and the function f of x at this x value is almost 0. We can look at this graphically. So that is the root value we got when we use this numerical methods using Newton-Raphson or Newton's method. To summarize, in this video we presented Newton's method to solve nonlinear equations. And Newton's method is a popular method to solve nonlinear equations, and it belongs to a group called open domain methods. Newton's method generally converges rapidly and is a popular method. But Newton's method requires the evaluation of the derivative. In the next video, we can look at another open domain method which does not require the evaluation of a derivative, which is called the secant method. If you have any questions, please post it. Thanks for watching the video.